Off the coast of Luzon, far beneath the waves of the South China Sea, lies a 1,000-kilometer trench marking a great tectonic collision, about 620 miles. This is no ordinary undersea ditch. It is the Manila Trench, a deep slumbering megathrust where the ancient Eurasian Sunda Plate is being driven under the Philippine Mobile Belt. For decades, this boundary has quietly stored immense strain as two enormous slabs grind together. Now scientists ask, if the Manila Trench were to wake with a great rupture, how bad could it be? The questions are urgent because the inevitable answer involves far more than just a tremor under the sea. It could mean a towering tsunami racing toward packed coastlines. The Manila Trench is simply the ocean floor signature of a vast subduction system. It runs roughly north-south off western Luzon and neighboring islands, linking two grand collision zones at its ends. To the north, it meets the Taiwan collision system. To the south, it curves toward the complex Mindoro-Palawan collisional zone. Geologists emphasize that this is no single line or simple fault. The trench is up to a few tens of kilometers wide, roughly a dozen to several dozen miles, and bends at its tips, reflecting deep plate geometry. Modern surveys show that as it approaches 18 degrees north latitude, the trench swings slightly northeast, and south of 14 degrees north latitude, it trends southeast. In other words, Manila's outline on the map hints at structural changes along its length. Along this undersea scar, one side is the old South China Sea basin of the Sunda Plate, the other side is the Luzon Arc and Forearc of the Philippine Mobile Belt. In some places, the downgoing slab is topped by a thick sediment pile, while elsewhere it plunges under thin or even vanished crust. This along-strike variation, accretionary in the north and erosive in the south, is clear from modern bathymetry and seismic imaging. In short, Manila is a boundary zone stretching over 1,000 kilometers, changing character as it goes, far more complex than a simple crack. Beneath that long trench, enormous forces are at work. The process is the classic subduction engine. The oceanic lithosphere plunges down into the mantle and, along the interface with the upper plate, stress builds. Think of it this way. Each year, the two sides converge by many centimeters, only a few meters since the last earthquake. Geodetic studies confirm roughly 90 to 100 millimeters per year, about 9 to 10 centimeters or about 4 inches annually, especially in northern Luzon. Where the fault is stuck, which appears to be most of it, that motion is not released gradually but accumulates as elastic strain. When friction finally gives, the whole interface can break. It is why subduction zones are the planet's most powerful earthquake factories. As one overview puts it, when the oceanic plate keeps diving, intense stress accumulates at the plate boundary. When this stress exceeds the frictional strength, it is released as an earthquake. Manila is no exception. Its megathrust stores energy until it snaps. Because the Manila megathrust is so large and shallow, any massive slip has the potential to be catastrophic. Subduction earthquakes differ from other faults mainly in scale. Their rupture planes can span hundreds of kilometers and are only a few tens of kilometers deep, so when they slip, they can push up entire sections of the seafloor. Even a moderate rupture here could displace a column of seawater. In the past, similar margins have unleashed truly giant earthquakes and tsunamis. Consider that in recent decades, subduction zones in places like Indonesia have produced ruptures up to 1,000 kilometers long that generated devastating tsunamis. For Manila, we know the interface is long, shallow, and holds a lot of locked strain. In fact, because no big Manila Trench earthquake has happened in centuries, scientists estimate tens of meters of slip deficit have built up on that plate interface. More than 30 meters of missing slip, according to one study, equivalent to an enormous magnitude 9 release. That is why experts treat this trench as more than a curiosity. It is a potential source of very large earthquakes and tsunamis if the conditions align. Exactly how alarming this system is has been debated, but on balance, the signs set Manila apart as a major tsunami threat. Consider first its length and coupling. Segments of the Manila Fault have presumably been locked for a long time. As Chu and colleagues note, no earthquake above about magnitude 7.6 has been recorded on this megathrust since the 1560s. That century-long silence strongly implies the plate interface is mostly stuck and loading strain rather than creeping quietly. Similarly, modern global positioning system and focal mechanism studies show the overriding plate is under shortening, not sliding freely. All told, the slab is highly coupled. In other words, it is a spring waiting to uncoil. And it converges very rapidly, up to 90 to 100 millimeters per year, about 9 to 10 centimeters, or about 3.5 to 4 inches, in the north. That rate is comparable to or faster than the Sumatra or Japan zones that have produced recent giant earthquakes. In short, Manila's engine is powerful and long frozen. Fault models treat each of its three main segments, roughly 14 to 16 degrees north latitude, 16 to 19 degrees north latitude, and 19 to 21.7 degrees north latitude, as capable of producing very large earthquakes. Simulations of tsunami generation allow for events up to magnitude 9 in those models. That generates real alarm. Even a magnitude 8 or higher event would be damaging, and a full-length rupture could have basin-wide effects. Still, careful scientists caution that the Manila Trench is not guaranteed to break in one perfect split. Its irregular geometry may actually inhibit a single superrupture. For example, recent seismological imaging shows a steep slab tear right around 17 degrees north latitude, where a fossil-spreading ridge, the Scarborough Seamount Chain, is subducted. In effect, the downgoing plate bends sharply and possibly tears there. Likewise, the trench is curved and segmented. The four-arc structure, sediment supply, and even a chain of seamounts known as the Scarborough Ridge change character by latitude. Geologists have explicitly divided Manila into at least three structural segments based on these features. In practice, each of these could act as a barrier that stops a rupture from crossing. Several modeling studies have found that bend and tear zones might break the trench into subregions. By contrast, other models that assume a nearly straight, uniformly locked fault allow the whole thing to break together. The truth is likely somewhere in between. In hazard assessments, experts often explore multiple scenarios, from one-segment ruptures to hypothetical mega-events, precisely because the real behavior is uncertain. The takeaway is that while the potential exists for a continuous, monstrous earthquake, it is not a foregone conclusion that the trench will simply snap all the way like a single crack. That uncertainty must temper expectations. So could Manila really produce a magnitude 9 earthquake? Some studies say it cannot be ruled out, while others think a long rupture is unlikely. On the extreme side, a number of worst-case models have simulated magnitude 9.0, magnitude 9.2, or even magnitude 9.3 events along Manila's interface. In these scenarios, the rupture spans nearly 1,000 kilometers, akin to the 2004 Sumatra-Andaman earthquake. Researchers argue there is no reason to rule out a magnitude 9 under Manila's long locking and high strain. That interpretation draws an analogy to Sumatra before 2004, an apparently quiet margin that surprised the world with a magnitude 9.2 event after centuries of seemingly little activity. On the other hand, many studies suggest the geometry of Manila might cap the rupture at roughly magnitude 8 to 8.5. Those studies point to strong along strike variations, bends, tears, and subducted features as likely breaking the fault into smaller pieces. In short, while a magnitude 9 scenario appears in some hazard papers, it is far from universally accepted. A truly gigantic earthquake is one possibility among several, not a certain forecast. As one researcher puts it, magnitude 9 is a worst-case edge of the envelope, scientifically plausible, but not necessarily probable. Even setting aside the largest theoretical rupture, lesser segments breaking could still be devastating. Imagine a magnitude 8.7 or 8.8 earthquake on just one section of the trench rather than the full length. That would be the worst case under a segmented fault interpretation, still enormous. Such a partial rupture would directly unload its energy on the nearest coastline. Western Luzon and adjacent lowlands would be hit hardest, receiving the strongest shaking and initial tsunami waves within minutes of the rupture. Just because it is partial does not mean safe. In fact, simulations of segment ruptures show that a magnitude 8.5 to 8.8 event off West Luzon could easily send multi-meter waves ashore, about 33 to 29 feet high. The largest flooding would be right along that segment, and it would spread out from there. In particular, coasts near the rupture, perhaps parts of Ilocos, Zambales, or Palawan, could face rapid inundation. The models reviewed in one recent study all show tsunami peaks measured in many meters, roughly several tens of feet, along the nearest shores, even for a single segment event. Farther across the sea, the waves would still travel, but with diminishing intensity. The point for emergency planners is that minutes count. Under the partial rupture scenario, communities closest to the quake would have almost no time to escape the brunt of the tsunami. Now consider the full rupture scenario. If a long, contiguous section of Manila broke as one, the South China Sea could see a basin-spanning tsunami. Hydrodynamic models agree this is a nightmare case. In numerical tsunami simulations, a magnitude 9 class event along Manila's entire fault has produced wave heights up to about 10 meters, roughly 33 feet on western Luzon, Taiwan, southern China, central Vietnam, and Palawan. Such wave height is enough to flood kilometers inland, roughly up to about 1.2 miles or more in low-lying areas depending on terrain. In these simulations, the highest waves tend to line up along direct ray paths. For example, West Luzon gets hit within an hour, and even farther shores like southern China and Vietnam feel multi-meter waves a few hours later. Other work, including a study focused on Vietnam, finds travel times of roughly 2 hours to reach central Vietnam from a large Manila earthquake. The energy can wrap around islands and concentrate through bathymetry into harbors and bays, making impacts highly variable. Overall, the scientific models show that if Manila ruptured fully, swaths of the South China Sea rim from North Luzon up to Hainan Island and down to Vietnam could see a destructive tsunami. Maps of these worst-case waves look bleak, with waves several meters high, often in the range of about 5 to 6 meters, or about 16 to 20 feet, running ashore in places normally bustling with people. In short, if Manila's full length ever ruptured as one, it could generate a trans-basin tsunami on the order of about 10 meters, roughly 33 feet, classifying it among the Great Pacific-scale tsunami sources. Who would feel the quake and tsunami first? If a huge rupture happened, the western shore of Luzon, essentially minutes from the trench, would face the immediate threat. Coastal towns in Ilocos, La Union, Pangasinan, and Zambales would feel the shaking first and see the first waves. For them, evacuation time could be less than 30 minutes or even just minutes. Further out, as the waves propagate, the hazard remains severe, but on a longer clock. Southern Taiwan and China's Hainan and Guangdong coasts would start to see waves a couple of hours later. Central Vietnam's shores might be hit about 2 to 3 hours after the event. The entire western Philippine archipelago, including Palawan and the Visayas' west coast, could feel strong waves within about 1 to 2 hours. This distinction of minutes for near zones and hours for distant coasts is important. Emergency planners stress that if a large Manila earthquake occurred, people closest to the trench could have virtually no warning beyond seconds, whereas those across the sea might have an hour or two to reach higher ground. Actual wave heights and arrival times depend on exactly where the rupture starts and which segments fail, so any evacuation plan must consider multiple scenarios. But the general pattern stands. Western Luzon faces an immediate threat, while the broader South China Sea basin is in danger within a couple of hours after shaking. How does this hazard fit with Philippine history? Notably, no one has ever observed a magnitude 9 earthquake in Philippine historical records. The Philippine Institute of Volcanology and Seismology has no entry for a magnitude 9 event in written annals. But that does not mean the threat is unreal. Even merely great earthquakes have caused devastation. For example, in August 1976, a magnitude 7.6 earthquake struck the Moro Gulf off Mindanao, generating a tsunami that killed thousands, often estimated at over 6,000 fatalities along the Sulu and Salib Seas. Similarly, the magnitude 7.6 earthquake under northern Luzon in July 1990 flattened parts of Baguio and Pangasinan, causing nearly 2,500 deaths. These are the nation's worst disasters of the modern era, and they were both well under magnitude 8. The reason Manila's worst case is taken seriously is precisely because events an order of magnitude smaller have proven deadly. Importantly, the Philippine Institute of Volcanology and Seismology itself warns that ancient tsunami deposits in parts of Manila suggest past waves reached inland areas, and that Manila Trench ruptures are among the plausible sources. In other words, geology hints that great tsunamis have impacted the Philippines, even if written records are lacking. Taken together, the historical pattern is clear. The Philippines is no stranger to monstrous earthquakes and tsunamis, so the idea of a magnitude 8 to 9 event offshore, while extreme, cannot be dismissed. In the end, the Manila Trench might stay quiet for decades to come. Earthquakes cannot be precisely predicted, but what matters is risk, not timing. All the evidence, including plate convergence, locked fault patches, geological clues, and modeling, tells us this is a real megathrust with enough accumulated strain that the worst case cannot be ignored. Crucially, the message from scientists is one of preparedness, not panic. We know where the danger could come from, so coastal hazard maps are being drawn and tsunami drills are conducted. The first defense is awareness and planning, including evacuation routes in Ilocos and Palawan, building codes in Luzon, and early warning systems around the South China Sea. Residents of western Luzon and the South China Sea rim should know how fast waves could arrive. If a large earthquake happened, minutes would count. Regional research urges exactly that approach. Treat Manila as a potential source and plan accordingly. The South China Sea basin is ringed by tens of millions of people and critical infrastructure. In that context, an unforeseen Manila megathrust earthquake, whether magnitude 9 or a high magnitude 8, would be devastating. The only real mitigation is preparation. The Manila Trench is not doomed to produce a megaquake next year, but it deserves vigilance. It is a sleeping giant worth mapping carefully in hazard models so that if it ever does stir, communities will be ready.